Usually when we look at like massive feats of human engineering, a suspension bridge, for example,
Right.
there is this expectation of visual logic. Like, you can see the thick steel cables, you can trace the massive concrete pillars anchoring everything deep into the bedrock, and your brain just naturally understands the physics.
Yeah, it makes physical sense to the human eye.
Exactly. You look at it and think, okay, that's what is holding the weight. That is how this structure survives a hurricane. The structural integrity is just completely intuitive.
Right, because we evolved to understand gravity and tension. When we look at a bridge, our brains are doing these like subconscious physics calculations to validate that it's safe.
Which is deeply comforting, but then you step into the world of artificial intelligence.
Oh yeah, completely different story.
Right. Specifically, you look at these massive large language models that are fundamentally altering our society, and suddenly that visual intuitive logic it completely evaporates.
Hmm.
We are looking at a mathematical landscape that is, well, entirely invisible. It's highly erratic, and it operates in dimensions our brains literally cannot picture.
Yeah, I mean, we were talking about spaces with thousands, sometimes tens of thousands of dimensions.
It's wild.
It is the absolute definition of a mathematical tightrope walk. And unlike a bridge, there are no steel cables to hold it up if the math starts to wobble.
Welcome to this deep dive. If you are listening right now, you might be one of the millions of people interacting with AI daily, and maybe you're wondering how models like GPT-4, Llama, or Claude actually function under the hood.
Right, beyond the magic tricks.
Exactly. We aren't going to talk about the marketing buzzwords today, and no philosophical debates about sentience either. We are going straight into the microscopic plumbing. Today, we have a fascinating stack of sources detailing the highly specific, deeply complex mathematical architecture of large language models.
Our mission for this deep dive is to explore the hidden mechanisms of that plumbing. We are going to unpack how seemingly microscopic engineering choices,
Like really tiny tweaks.
right, like changing the order of a single equation or taking a massive grid of data and just violently squashing it flat. We want to show how those are the exact reasons why a billion-parameter AI can actually learn to speak.
Because without these specific workarounds, these models wouldn't just be, a little dumb.
No, they would immediately collapse into mathematical garbage.
I promise you we are going to translate some seriously dense concepts today. Things like gradient flows, tensor flattening, mathematical variance. We're going to turn those into intuitive aha moments for you. The story of how we got here is just incredible. It's not just a story of throwing more computer chips at a problem.
Far from it.
Yeah.
If we connect this to the bigger picture, we are fundamentally looking at how human engineers wrestled with chaotic, unstable mathematics and forced it to behave.
Yeah.
It's a story of brutal trial and error, brilliant deductive reasoning, and frankly, hardware-level illusions.
Okay, so let's unpack this right from the foundational building block. To understand any modern AI, we have to talk about the transformer architecture.
The bedrock of all of this.
Right. Specifically, our sources point heavily to a microscopic cross-section of this architecture called the residual block and a critical mechanism inside it called layer normalization, or just LayerNorm.
Yeah, LayerNorm.
And the sources outline this massive industry-wide war over exactly where to put this single line of math. There's the original approach, post-LN, and the modern standard, pre-LN.
Right. And to conceptualize this, we need to understand how data physically moves through a neural network.
Okay, set the scene for us.
Imagine a massive multi-lane highway. In the architecture of a transformer, we call this the residual stream. The data, let's say a sentence you just typed into a chatbot, travels down this highway.
Cruising along.
Exactly. But the highway itself doesn't do any thinking. To actually process the text, the data has to take side roads, which we call sublayers.
And these side roads are where the heavy lifting happens, right? The complex algorithms like self-attention, where words look at other words to figure out context. Or the feed-forward networks.
Those are the side roads. The data exits the highway, goes through a massive factory of matrix multiplications in that sublayer, gets transformed, and then merges back onto the main highway to continue its journey to the next layer.
Okay, I can visualize the traffic flow. Highway, exit ramp, factory on-ramp, back to the highway. So where does layer normalization fit into this?
From my understanding, normalization is basically a mathematical stabilizing mechanism. It keeps the numbers from spiraling out of control.
That is its sole purpose. As data gets multiplied and added millions of times in those factories, the numerical values can get incredibly large or incredibly small.
Right.
Layer normalization calculates the spread of those numbers and squashes them back to a safe baseline scale. Now, in the original Transformer paper published by Vaswani and colleagues back in 2017,
The paper that started all of
the
this.
paper that arguably started this entire modern AI boom, they used post-LN, post meaning after the factory.
Exactly. In post-LN, the LayerNorm checkpoint is placed after the transformed data merges back onto the highway. So mathematically, the data goes through the side road, gets added back to the original highway traffic, and then that entire merged stream of traffic is forced through the normalization checkpoint.
So, if we think of this like constructing a massive skyscraper, post-LN is like building an entire floor, putting up the drywall, the complex wiring, the plumbing, everything,
Right.
and then violently stress testing the entire finished floor to make sure it doesn't fall over before you move on to build the next floor.
That is a highly accurate way to picture the structural logic.
But the sources say almost the entire industry abandoned this.
Mm.
The titans of today, models like GPT-3, PaLM, LaMDA, they all use pre-LN. They flip the order.
They move the checkpoint. In pre-LN, the layer normalization is placed before the sublayer factory, entirely off the main highway.
Oh, okay.
Yeah, the data on the highway takes the exit ramp, immediately hits the normalization checkpoint, goes through the factory, and then merges back onto the highway.
Leaving the main highway completely untouched by the normalization process.
The central highway never experiences a single speed bump.
Wow. Going back to the skyscraper, pre-LN is like stress testing the raw steel beams on the ground before you bolt them onto the mainframe, but leaving the central skeleton of the building completely alone to just rise into the sky, unbothered.
Exactly.
But structurally, it's the exact same components, right? We haven't added any new math. We just moved the inspector to a different part of the assembly line. Why does that simple swap matter so much?
Because that single swap dictates whether a massive model can be trained at all.
Really? Just moving it.
It is literally the difference between life and death for a deep neural network. To grasp the severity of this, we have to look at the fatal flaw of that original post-LN design. It suffers from a dual catastrophe during the training process.
A dual catastrophe. That sounds intense.
It is. You get simultaneous gradient vanishing at the bottom of the network and gradient explosion at the top.
Ice and fire happening at the exact same time. That sounds like the physics of the model are just tearing themselves apart. Let's break down the ice first. Why does the bottom of the network freeze up?
Well, we have to introduce how AI actually learns. It doesn't learn on the forward journey. When your sentence travels down the highway and reaches the end, the AI makes a prediction, say, guessing the next word.
And it's usually wrong at first.
Very wrong. It calculates how wrong it is, which we call the error. To actually learn, it has to send a signal, a gradient backward through the entire network, from the output all the way down to the input, telling every single layer how to adjust its weights. This is called backpropagation.
It's like a boss at the top of a corporate hierarchy finding a massive mistake on a final report and sending a memo down the chain of command telling every manager to fix their department.
That's a great way to look at it.
Oh.
And in post-LN, that memo runs into what researchers call the forward pass illusion.
Okay, what's that?
When the data is moving forward, everything looks beautifully stable. The sublayer factory does its work, adds its new data to the highway, and naturally, the variance, the raw energy or spread of those numbers, gets bigger. 1 + 1 = 2.
Makes sense.
But post-LN, sitting on the highway, violently squashes that energy back down to 1. On the surface, the forward traffic looks completely controlled.
The inspector is keeping the building looking neat. The numbers never get too big. But what happens when the boss sends the correction memo backward?
That is where the math turns deadly. Because the calculus involved in backpropagation, the derivative of that LayerNorm function acts as a severe dampener.
A dampener.
Yeah. Every single time the backward signal passes through a post-LN checkpoint that previously squashed the variance, the returning error signal is shrunk by a factor of roughly 1 over the square root of 2.
1 over the square root of 2. So you're multiplying the signal by roughly 0.7. You're losing 30% of the boss's memo at every single floor.
Every single floor. Now imagine a deep model with 50 or 100 layers. That error signal has to pass through 100 consecutive dampeners.
Oh, wow.
By the time that signal reaches the bottom layers, the entry-level workers closest to the input, you are multiplying 0.7 by itself 100 times. The resulting number is essentially 0. The sigil vanishes.
So the bottom layers hear absolutely nothing. They have no idea what they did wrong, so they don't change their weights. They just stop learning entirely. The bottom of the network is paralyzed.
Complete paralysis.
Yeah.
But remember, we said this is a dual catastrophe. While the entry-level workers are frozen, the top-level executives are catching fire.
The gradient explosion. How is that possible? If the middle managers are dampening the signal, how is the top of the network getting blown up?
Look at the architecture at the very top. The highest layer parameters don't have 100 layers of normalization checkpoints behind them. They are sitting right next to the output.
Right, they're right next to the boss.
It's exactly. According to a pivotal 2020 paper by Microsoft Research Asia detailed in our sources, these top layers in post-LN actually see their gradient expectations amplified linearly based on the total number of layers.
Wait, let me logic this out. When the network is first turned on, the weights are totally random. The first guess is going to be astronomically wrong.
Very wrong.
So the boss screams at maximum volume. The top layer, sitting right next to the boss, takes the absolute brunt of that scream before any LayerNorm has a chance to dampen it.
And it gets worse. Because the forward pass in post-LN allowed the variance to swell right before the checkpoint, the mathematical instability accumulates. The Microsoft researchers proved that the top layer experiences an amplification of the error signal proportional to the total depth of the network.
Meaning?
If you have 100 layers, the top layer's updates are 100 times more volatile on day one.
Whoa, the parameters just get blown out into massive random numbers.
They get completely shredded. And once the top layer parameters explode into garbage, what happens on the next forward pass? They take perfectly good data, multiply it by garbage, and send corrupted data to the output. The network is permanently brain damaged within the first few steps of training.
Unless engineers intervene. I've read about this agonizing process called warm-up. This is basically bomb defusal, isn't it?
It is incredibly tedious. To prevent the top layers from exploding, engineers use warm-up. They manually override the learning rate. For the first few thousand steps of training, they force the network to learn at an incredibly slow microscopic pace.
So they basically whisper the boss's memo.
Exactly. Slowly, step by step, they turn up the volume over days or weeks of training until the network stabilizes.
But doing that requires guessing the exact right hyperparameters. If you turn the volume up too fast, it explodes. If you keep it too low, it takes months to train and wastes millions of dollars in GPU time. It sounds like an absolute nightmare.
Which is precisely why the industry aggressively pivoted to pre-LN. The elegance of pre-LN is how it fundamentally rewires the physics of that highway to solve both the ice and the fire naturally.
Because in pre-LN, the normalization checkpoint is moved entirely off the highway onto the exit ramp. The main road is just pure, unobstructed addition.
And in the realm of calculus, the derivative of pure addition is just 1.
Meaning the signal doesn't degrade. If the boss sends a memo with a volume of 10 and it travels backward down a highway of pure addition, 10 multiplied by 1 is 10. The entry-level workers at the very bottom receive the exact same unmitigated signal as the executives at the top.
The vanishing gradient problem is completely eradicated. The bottom layers can learn at full speed from day one.
But hold on, we have to look at the other side of the equation. In post-LN, you said the normalization was acting as the inspector, squashing the raw energy of the data to keep the forward pass stable. If pre-LN removes the inspector from the highway entirely, doesn't the energy just constantly snowball? Layer 1 adds some data, the variance is 2. Layer 2 adds more, the variance is 3. By layer 100, the data's energy is 100. It's compounding endlessly.
It is snowballing tremendously. The variance on the main highway scales linearly with depth.
Then how does the network not blow up? If the energy is 100 times larger by the end of the network, shouldn't the top layers be even more volatile than before?
This is the brilliant paradox of pre-LN. The variance on the main highway does explode. But remember where we put the inspector. We put the LayerNorm on the exit ramp right before the sublayer factory.
Ah, okay, let me trace the path. The boss sends the backward signal down the highway. The signal is completely undampened. But to actually update the weights in the top layer factory, the signal has to turn off the highway and travel backward up the exit ramp.
Yes.
And that is where it hits the LayerNorm.
And what does LayerNorm do when it sees massive variance? It dampens the signal proportional to that variance. At the top of the network, the highway variance has snowballed into a massive number.
Right.
So when the error signal turns off the highway into the top layer factory, the pre-LN checkpoint sees that massive variance and severely dampens the gradient entering the factory.
That is unbelievably elegant. The snowballing energy on the forward pass creates its own natural braking system for the backward pass.
Precisely.
The higher up the network you go, the bigger the variance, and therefore the harder the brakes are applied to the gradients entering the sublayers. The top layers are naturally suppressed from exploding, while the bottom layers get the full, raw feedback via the unblocked highway.
It is a self-regulating physical system. No manual warm-up bomb defusal required. The network just balances itself out of the box.
Okay, that sounds like a total victory. But in engineering, there is no free lunch. What is the hidden cost of this stability?
Well, the hidden cost is a phenomenon known as the effective depth problem. It comes down to how much the network can actually change its mind at the higher layers. Let's use an analogy from the source literature. Imagine the data on the highway is a bucket of water.
All right, I've got a bucket.
In the old post-LN system, every time you pass a layer, it's like adding a scoop of salt to the water. But then the normalization forces you to dilute the bucket back to its original volume and concentration.
Okay.
Because of that constant resetting, every time you add a new scoop of salt at a new layer, it drastically alters the chemical makeup of the bucket. Every layer contributes equally to the final flavor.
So the 100th layer has just as much impact as the first layer.
Exactly. But in pre-LN, remember, the highway variance is just snowballing. We're continually adding salt to the bucket without ever diluting it. Layer 1 adds a scoop, the variance is 2. Layer 10 adds a scoop, the variance is 11.
I see where this is going.
By the time you get to layer 99, the bucket already has 99 massive scoops of salt in it.
Oh man, when layer 100 adds its one little scoop of salt into a bucket that already has 99 scoops, that new salt is only changing the overall flavor by like 1%.
We call this passivation. Because the highway variance grows so large, the outputs of the higher layers represent an increasingly tiny fraction of the total signal. The higher layers become mathematically muted. They lose their ability to meaningfully shift the trajectory of the data.
So pre-LN is technically weaker. Like, it can't squeeze as much raw learning power out of its top layers because their voices are drowned out by the accumulated noise of the lower layers.
In terms of raw representation capacity, yes. Post-LN is theoretically smarter per layer.
Did engineers just accept that? It feels like leaving horsepower on the table.
Some didn't. A few years ago, researchers trying to resurrect the old post-LN architecture. They developed a technique called DeepNorm, where they used incredibly complex mathematical initializations to perfectly balance the weights from day one, trying to get that high representation capacity without the explosions.
Did it work?
Theoretically, yes. But practically, the industry looked at the sheer pain of tuning those fragile post-LN networks, looked at the absolute rock-solid plug-and-play stability of pre-LN, and decided the trade-off was more than worth it.
Makes sense.
If pre-LN is a little weaker per layer, the solution is simple. Just add more layers. Compute is cheaper than engineering headaches. That is a major reason why we have these 100-plus layer behemoths today. We brute force the capacity issue by building taller skyscrapers.
That is a masterclass in pragmatic engineering. Stability trumps theoretical perfection. Okay, so we've definitively solved where to put the normalization checkpoint. But the sources reveal an entirely separate war over what kind of normalization to actually use. And this brings us to a massive divide between the AI that looks at pictures and the AI that reads text.
The divide between computer vision and natural language processing. It is a fascinating clash of philosophies.
From what I gather, if you are building an AI to recognize objects in photos, you use something called batch norm. It is the absolute gold standard. But if you try to use batch norm on text, it fails catastrophically.
Right. Completely falls apart.
The text models reject it entirely in favor of LayerNorm. To understand why, we have to look at what these two techniques are actually measuring. The source material outlines an analogy called the class exam. Let's walk through that.
Let's set the scene. You have a classroom of students taking final exams. In our neural network, the students represent our batch, the different samples of data moving through the network simultaneously. The subjects they are tested on, math, English, physics, represent the features or the hidden dimensions of our data.
So I've got student A, student B, and student C, all taking tests across multiple subjects.
Right. Batch norm operates like a teacher grading on a curve. It isolates a single subject, say math, and looks at every student's score in that one subject. It calculates the class average for math, and then normalizes everyone's score based on that global average.
So it ignores everything else.
It completely ignores how student A did in English or physics. It only cares about the distribution of math scores across the entire batch of students.
Now, I can see why that works beautifully for images. If you are training a model on a batch of 100 photographs of faces, and you are trying to detect the edge of a nose, That edge is likely going to be in roughly the same pixel location across all 100 photos.
Exactly.
It makes complete sense to calculate the average intensity of that specific pixel across the entire batch. The spatial structure is highly consistent.
Images are uniform grids. Pixel 500 is always pixel 500. But language is entirely unbound. Language is messy, varying in length and structure. LayerNorm, on the other hand, acts like a personal report card.
Okay.
It isolates a single student, student A, and normalizes their scores across all of their own individual subjects, math, English, physics. It completely ignores the rest of the classroom. It only cares about student A's internal distribution of skills.
So LayerNorm looks at a single word and normalizes the thousands of hidden dimensions inside that word, ignoring all the other words in the batch. Okay, I understand the mechanics, but why does grading on a curve batch norm fail so spectacularly when applied to text?
There are three fatal mathematical breakdowns. The first is what we call padding pollution. Think about our image data set. Every picture can be perfectly cropped and resized to 256 by 256 pixels. They are mathematically uniform. But sentences. You might feed the network one sentence with 5 words and another sentence with 50 words.
But the GPU, the actual physical hardware doing the math, can't process jagged, uneven data. It needs perfect rectangular matrices to run its calculations.
It demands symmetry. So, to force text into a rectangular matrix, engineers use a trick called padding. They take the short 5-word sentence and they add 45 invisible, meaningless zero-value tokens to the end of it until it matches the exact length of the 50-word sentence.
Ah, I see the collision course here. If batch norm grades on a curve, it looks across the batch at a specific position. It takes the 20th word of every single sentence in the batch and averages them together. But for the short sentence, that 20th word isn't a word at all. It's a padding 0.
It is a mathematical void. Batch norm starts blindly averaging real, meaningful vocabulary features with absolute nothingness. It totally destroys the statistical distribution. It would be like calculating the class average for the math exam, but including 40 empty desks in the calculation.
Wow. That would drag the class average down to failing and completely ruin the curve for the actual students who took the test. The normalization gets poisoned by the padding.
Padding pollution is a major hurdle. But let's complicate that picture a bit. Let's pretend we magically solve the padding problem.
Yeah.
Let's say we have a data set where every single sentence happens to be exactly 10 words long. No padding required.
Okay.
Batch norm still fails because of the second issue, semantic misalignment.
Semantic misalignment. Let me logic this out. Even without zeros, batch norm is still averaging words based on their structural position. It takes the first word of my sentence and the first word of your sentence and finds the mean. But the first word of my sentence might be the pronoun she, and the first word of your sentence might be the adverb suddenly. Averaging a pronoun and an adverb, I mean, it's mathematically possible to add those vectors together, but conceptually, it's absolute garbage.
It is entirely meaningless. You are forcing the alignment of concepts that have absolutely nothing to do with each other solely because they happen to be the first sound out of someone's mouth. The statistical average of she and suddenly does not help the AI understand either word better.
Right.
LayerNorm bypasses this entirely. It only looks at the word she and normalizes its internal dimensions against itself. It doesn't care what the first word of the next sentence is doing.
So batch norm corrupts the meaning by forcing arbitrary alignments. That makes sense. What is the third breakdown?
The third breakdown is the most practical one. It's called the inference disaster, and it happens when you actually release the model into the real world. During training, batch norm calculates these global class averages and saves them to use later.
Right. It saves the curve.
But think about how an LLM actually operates when you are chatting with it online. It generates text, one single token at a time. We call this continuous batching.
Right. It doesn't spit out a whole paragraph at once. You watch it type word by word.
Because it is generating dynamically, the batch size, the number of users the server is handling simultaneously, is fluctuating every millisecond. Sometimes, late at night, the server might only be handling a single user asking a single question. The batch size is 1.
And batch norm relies on a large, stable classroom of students to calculate a meaningful curve. If only one student shows up to the final exam, batch norm mathematically panics. You cannot calculate a curve for a single data point. The math literally breaks down.
Exactly the problem. The saved training statistics suddenly don't match the real-world deployment realities. LayerNorm, however, is immune to this. Because it acts as a personal report card, it only requires the data inside that single token to do its job. Whether there is one user or 10,000 users hitting the server, LayerNorm functions identically.
Okay, the evidence is overwhelming. Batch norm is fundamentally incompatible with the chemotic nature of text. LayerNorm is the undisputed king of language models. But this actually brings us to a conceptual wall. I have to push back on LayerNorm now based on the very logic we just established.
Let's hear it.
We agreed that LayerNorm is a personal report card. It averages a single student's scores across math, English, and physics. Translating that back to the AI, LayerNorm takes a single token, let's say the word apple, and it calculates the average across its 4,096 internal dimensions.
Right.
But isn't that mathematically absurd on its face? If dimension 1 represents nounness, dimension 2 represents emotional tone, and dimension 3 represents plurality, averaging them is literally mixing apples and oranges. How does calculating the mean of completely different conceptual traits help the AI learn anything? You're just mashing distinct features into a gray paste.
That is a highly logical pushback, and it strikes at the very core of how humans assume AI represents knowledge. Your critique makes perfect sense, but it relies on a flawed premise, which the assumption that dimension 1 is cleanly nounness and dimension 2 is cleanly emotional tone.
They aren't. I thought the whole point of a feature dimension was to track a specific trait, like the number of bedrooms in a house dataset.
In traditional small-scale machine learning, you are correct. One column in the spreadsheet equals one clean feature. But large language models do not operate in that realm. They utilize something called distributed representation. In an LLM's 4,096 dimensional space, a single dimension does not hold a single isolated concept.
Wait, really?
Yeah, if you extracted dimension 42 and look at it in a vacuum, it would look like pure statistical noise. It means nothing on its own.
Then where does the meaning actually live?
The meaning of a token is stored in the angle and the proportion of all 4,096 dimensions resonating together simultaneously. The concept of an apple isn't sitting in a designated box. It is a highly specific harmony played across 4,096 strings.
Wow.
Because every single dimension participates in every single concept to some tiny fractional degree, the dimensions themselves are statistically homogeneous.
Oh, wow. Okay, so they aren't apples and oranges. They are just 4,096 identical strings vibrating at different frequencies to create a chord. Averaging them doesn't destroy the meaning because no single string holds the meaning anyway.
That is the conceptual shift required to understand LLMs, and it reveals the true underlying purpose of LayerNorm. It isn't trying to find the semantic average of the word. That's not the goal. It is functioning purely as a physical safety valve.
A safety valve, like regulating steam pressure in an engine.
Precisely. Let's look at the attention mechanism, the part of the network that decides which words in a sentence are important. Attention relies heavily on the numerical magnitude, the raw size, of these vectors. If the numbers inside a token's vector get too large, if the energy of the token spikes because of some compounding mathematical quirk during training, that one token will become mathematically massive compared to the words around it.
It becomes a giant magnet.
It acts like a black hole. We call it an attention kidnapping. The mathematical formulas will latch onto that massive vector, and the AI will suddenly focus exclusively on that one word, completely ignoring the context of the rest of the sentence. The model's reasoning collapses.
Ah, so LayerNorm doesn't care about the meaning of the dimensions. It only cares about the overall volume of the token.
It calculates the average, energy, and the variance across the 4,096 dimensions, and it forcefully clamps the token's total energy back to a safe baseline pressure. Crucially, it preserves the direction of the vector in that high-dimensional space, the specific proportions between the 4,096 strings, which is what actually holds the semantic meaning, but it normalizes the magnitude, the volume. It stops any single token from blowing out the speakers.
That is a brilliant mechanical workaround. It's not a philosophical evaluation of the word. It's just a governor on an engine to keep it from redlining. And knowing that it's just a mechanical safety valve, well, that perfectly sets up the next massive evolution in our sources. Because engineers eventually realized they could make the safety valve significantly lazier, didn't they?
So lazier is perhaps the most accurate word for it. Around 2019, the AI research community had a massive revelation regarding the standard LayerNorm formula. If we look closely at the math, standard LayerNorm actually performs two distinct operations.
What are they?
First, it centers the data by calculating the mean of the 4,096 dimensions and subtracting that mean from every value, shifting the baseline to 0. Second, it scales the data by dividing by the standard deviation, which squashes the variance.
So it shifts the baseline, and then it squashes the spread.
But when researchers rigorously tested these two steps, they discovered something shocking. That first step, the centering, the subtraction of the mean, it is practically useless. It contributes almost zero value to the stability or the success of the model's training.
Wait, if the whole point is just to prevent the total volume from blowing out the speakers, why do we care where the absolute zero baseline is anyway? As long as the variance is squashed, the safety valve is doing its job.
That was exactly the realization. The model was doing millions of complex calculations at every layer just to find and subtract a mean that didn't fundamentally alter the learning trajectory. It was pure mathematical fat.
And in AI, fat is bad.
In the realm of AI training, fat translates directly to wasted GPU memory and wasted time. So the engineers stripped it out entirely. This evolution is called RMSNorm, which stands for root mean square normalization.
If we go back to the orchestra analogy, classic LayerNorm was meticulously checking the ambient room volume, shifting the baseline, and then checking the dynamic range of the music. RMSNorm steps in and says, look, I don't care what the ambient room volume is, just measure the total sound energy, the root mean square, and mathematically ensure it doesn't blow out the speakers. It's just scaling, no centering.
It drops the centering entirely. And to understand why this was such an industry-shaking big deal, we have to talk about hardware bottlenecks. People often think the speed limit of an AI is how fast the GPU can do multiplication.
Right, the raw processing power.
But often, the real bottleneck is memory bandwidth, how fast the GPU can read data from its memory chips and move it to the processing cores.
The commute time for the data.
Yes. To calculate classic LayerNorm, the GPU has to read the entire token vector from memory to calculate the mean. Then it has to read the entire vector again to subtract that mean and calculate the variance. 2 full trips to memory.
That sounds inefficient.
It is. By dropping the mean calculation, RMSNorm only requires a single pass over the data. It calculates the sum of the squares in one shot.
Cutting the commute time in half. How much time does that actually save in practice?
At the layer level, dropping the mean saves anywhere from 7% to 50% in computation time, depending on the specific hardware architecture.
50%. That is a staggering efficiency gain when you consider these models are training on trillions of tokens for months at a time.
It saves massive amounts of electricity and compute budget. And the effect on the model's actual intelligence or accuracy is practically zero. It performs identically to classic LayerNorm, just significantly faster. If you look at the architecture of the leading models today, Llama, Gemma, Mistral, DeepSeek, none of them use classic LayerNorm anymore.
It's just gone.
The original formula is a historical relic. They all utilize pre-RMSNorm. It is the absolute champion of modern LLM design.
We have spent a lot of time talking about the nuances of normalization, the flow of gradients, and the physical limitations of GPUs. But to truly grasp how these models process oceans of data at such blinding speeds, our sources mandate that we have to completely unlearn how we think about data itself. We need to talk about dimension mapping.
This is where we cross from complex engineering into structural philosophy. If we want to understand the ultimate triumph of LLM engineering, we have to let go of the traditional machine learning view of the world.
Let's establish that traditional view first. If I'm a data scientist building a standard old-school algorithm to predict house prices, my data set is a spreadsheet. A single sample, one row in my spreadsheet, represents one entire house. And the features, the dimensions of that sample, are the columns, the number of bedrooms, the square footage, the zip code. One house equals one complete sample.
That is the intuitive, human way to organize data. And naturally, when we transition to language, we try to map that exact same logic onto text. We intuitively want to say, okay, in natural language processing, a sample must be a single sentence, and the features must be the individual words that make up that sentence.
It makes logical sense. A sentence is a complete thought, just like a house is a complete entity. But the sources are very clear. That assumption is fundamentally wrong.
It is deeply incorrect. And if you hold on to that assumption, the internal mechanics of a large language model will remain entirely opaque to you. In an LLM, the sample is not a sentence. The sample is a single isolated token, just a fragment of a word.
A single word piece is the equivalent of an entire house in the database.
Yes, and the features, the equivalent of the square footage and the zip code, are those 4,096 hidden mathematical dimensions trapped inside that single token.
Let me make sure I'm fully absorbing this. When an LLM is reading a paragraph of text, the multi-layer perceptron, the dense feed-forward network that makes up the bulk of the model's brain, it doesn't look at a sentence at all. It just sees a massive bucket of highly complex, entirely independent mathematical objects.
To the feed-forward network, the concept of a sentence simply does not exist. It processes every single token entirely in isolation.
Wow.
It grabs token A, pushes its 4,096 dimensions through the massive factory of weights, and spits out an updated version of token A. Then it moves to token B and does the exact same calculation. The MLP does not know and mathematically does not care that token A and token B are physically sitting next to each other in a sentence.
That is mind-bending. The AI doesn't even know it's reading a book. It's just processing millions of floating 4,096 dimensional objects in a void.
Only the attention mechanism looks across the sequence to compare words. The overwhelming majority of the compute power, the MLPs, operates in total sequence blindness. And that specific realization that the bulk of the network doesn't care about sequence paved the way for the most aggressive, rule-breaking optimization in modern AI engineering, the flattening revolution.
Reading the sources on this flattening process honestly felt like reading a script for a bank heist. The engineers looked at the rules of data structure, realized those rules were slowing them down, and just completely broke them to steal back GPU processing power.
It's a phenomenal heist. Let's look at the mark they were trying to rob, the 3D tensor. Traditionally, data flows into a transformer block as a neat three-dimensional cube. You have the batch dimension, which is the number of distinct documents you're processing at once. You have the sequence dimension, which is the maximum length of those documents. And you have the hidden dimension, the 4,096 features.
Batch sequence dimension. A highly organized logical cube of data.
Highly organized, but as we discussed earlier with the padding problem, incredibly wasteful.
Right, because if document 1 is a short 100-word email and document 2 is a 4,000-word legal contract, you have to pump document 1 full of 3,900 zero-value tokens just to make the 3D cube perfectly square for the GPU.
And here is the brutal reality of hardware. The GPU does not know those are zeros. It still diligently performs thousands of complex matrix multiplications on every single one of those 3,900 empty tokens, pushing them through every layer of a 100-layer network.
Just churning through nothing.
Exactly. In real-world data sets, which are a chaotic mix of short text messages and massive articles, padding can waste anywhere from 30% to 50% of your total GPU compute capacity. You're literally burning millions of dollars of electricity to multiply nothingness.
So how did the engineers steal that compute back? If the GPU requires a perfect matrix, how do you eliminate the padding?
By annihilating the 3D tensor entirely, engineers developed a radical data preparation solution called packing. Instead of keeping documents separate, they take thousands of distinct, completely unrelated documents, say, a recipe for pie, a Python coding manual, and a historical essay.
And they just stitch them end to end into one massive, continuous string of text, a single million-token-long worm of data.
They just glue them together. Then they take a mathematical cleaver and blindly chop that massive worm into neat, perfectly sized chunks, let's say exactly 4,096 tokens long.
Blindly, without caring where the documents end.
Completely blindly. A single 4,096 token chunk might contain the trailing end of document A, the entirety of document B, and the opening paragraph of document C. But notice what is missing. There is absolutely zero padding. Every single token is real, meaningful data. It is a 100% pure, unadulterated matrix.
And because they stitched it all together, the shape of the data completely changes. The batch dimension and the sequence dimension are smashed together. That organized 3D cube is violently flattened into a 2D matrix. Total tokens by hidden dimension.
That's the flattening.
Okay, I see how that gives you 100% compute efficiency. No wasted zeros. But I have a massive problem with this. I understand that the MLP doesn't care about sequence. But the attention mechanism does.
Yes, it does.
The entire core philosophy of self-attention is words looking at other words in a sequence to gain contextual meaning. If you flatten everything into one continuous chunk, if you literally stitch my tax return to a Shakespeare sonnet and feed it to the attention mechanism as one sequence, the AI is going to cross-contaminate them. Romeo is going to start declaring his love for the IRS.
That is the exact reason why flattening sounds fundamentally impossible. If the attention mechanism views the chunk as one continuous sequence, Romeo absolutely will start reciting tax code. The semantic boundaries between the documents would be utterly destroyed, and the model would hallucinate wildly.
So how do they fix it?
This is where the engineers coded absolute magic at the lowest hardware level to save the semantics.
How? If the data is just a flat, borderless soup of text in the high-level memory, how does the AI know where the tax return ends and the sonnet begins?
Through a revolutionary, highly specialized algorithmic patch called Flash Attention 2 and a tiny array of numerical pointers known as QSequence.
Let's unpack that. QSequence.
It stands for Cumulative Sequence Lengths. In the old days, to prevent the AI from looking at certain words, we would send a massive mask matrix, a giant grid of ones and zeros, to block out the unrelated text. But sending giant masks defeats the whole purpose of saving memory.
Right.
So instead, the data loader sends the flattened text chunk, and right alongside it, it passes a tiny, incredibly lightweight list of index numbers. This list simply says, hey, document 1 ends at token index 500. Document 2 ends at token index 1200.
It's just a map of where the original borders used to be?
Exactly. And this map isn't processed by the high-level software. It is passed straight down to the physical silicon, the CUA cores on the GPU. The hardware itself reads those index pointers and builds invisible mathematical blast doors on the fly during the calculation.
Wait, the physical chip is enforcing the borders?
Yes. When the attention mechanism is processing token 499, which is in the tax return, the hardware allows it to look backward at the rest of the tax return. But the millisecond the processor moves to token 501, the first word of the Shakespeare sonnet, the hardware physically restricts the memory access. The computation is physically blocked from crossing that index pointer. Token 501 cannot see token 500.
That is staggering. So in the high-level software memory, the data is entirely flat and structureless to guarantee maximum processing speed. But deep down in the actual circuitry, the GPU is throwing up localized blast doors based on a cheat sheet of pointers, preventing Romeo from seeing the tax forms.
It is a dual reality system, conceptually flattened for speed, partitioned in silicon for semantics.
But there is one final piece of this puzzle I can't wrap my head around. What about the actual order of the words?
Word order.
Yeah, if the tax return is 500 words long, the first word of the sonnet is technically sitting in the 501st slot of the flattened array. How does the AI know it's the start of a brand new document, and not just the 501st word of a really long, boring story? How does it understand its position?
That is the absolute final layer of the heist, manipulating the position IDs. Modern LLMs understand word order through an incredibly clever mechanism called rotary position embeddings, or ROPE. Instead of just adding a number to a word, ROPE applies a mathematical rotation to the token's vector based on its position in the sequence.
Like rotating a hand on a clock face. The first word gets rotated a little bit, the second word gets rotated a little more.
Precisely. The angle of rotation dictates the word's physical position in the sentence. Now, when the data loader is preparing that flattened chunk of text, it doesn't just send the words. It sends a custom stream of coordinate numbers, position IDs. For the tax return, it counts normally, 1, 2, 3, all the way to 500.
And when it hits the sonnet,
The moment the data loader crosses the boundary into the Shakespeare sonnet, it forcefully resets the position ID counter back to 0. It tells the sonnet you are starting at position 1.
So the sonnet gets a fresh set of rotational coordinates.
Exactly. So when the ROPE algorithm fires up and starts applying its rotations, the first word of the sonnet behaves mathematically exactly like the first word of any sentence. Its vector is rotated as if it is at the absolute beginning, entirely regardless of the fact that it is physically sitting in the 501st memory slot of the flattened array.
If we pull all the way back and look at this from a bird's eye view, this is the ultimate pinnacle of LLM engineering. We completely destroyed the logical, human-readable structure of the data in the software to squeeze every last drop of speed out of the hardware. But we secretly, invisibly preserved the semantic boundaries using pointer arrays and coordinate resets deep in the circuitry.
It is the absolute definition of having your cake and eating it too in computer science. Engineers achieved the holy grail. 100% compute utilization of a perfectly dense, flattened matrix without sacrificing a single drop of semantic accuracy or context.
This has been an absolutely incredible journey through the invisible architecture of AI. Let me try to synthesize what we've unpacked today because the sheer density of the engineering is staggering.
It really is.
We started by looking at how moving a single normalization checkpoint just a few inches to the left, shifting from post-LN to pre-LN saved entire networks from catastrophic gradient vanishing and exploding top layers. It created an unobstructed highway for the AI to actually learn.
And we recognized the pragmatic trade-off. We accepted that this newfound stability came at the cost of the higher layers becoming slightly passivated by a snowballing variance, choosing reliable scaling over fragile perfection.
Then we explored the normalization wars. We discovered that grading on a curve with batch norm is a total disaster for text due to the mathematical voids of padding zeros and the sheer chaos of semantic misalignment. Instead, the industry-crowned LayerNorm, which acts purely as a mechanical pressure safety valve to keep individual tokens from kidnapping the attention mechanism, even if it means averaging apples and oranges in a high-dimensional distributed space.
which engineers then ruthlessly optimize into RMSNorm, stripping out the mean calculation entirely to save up to 50% on computation time by bypassing hardware memory bottlenecks without losing an ounce of performance.
And finally, we witnessed the complete structural breakdown of data itself. We watched engineers squash the very concept of sentences, flattening organized 3D tensors into giant borderless arrays to eliminate padding waste. They relied on flash attention, hardware-level blast doors, and rotary coordinate resets to keep the AI from hallucinating connections across stitched-together documents.
It is a beautifully chaotic, highly engineered symphony of workarounds.
For you, the listener, the ultimate takeaway here is that the magic of artificial intelligence isn't just found in amassing massive data sets or debating theoretical concepts of digital brains. The real magic, the concrete reason these models actually exist and function in the real world today, is found in these microscopic, brilliant, often rule-breaking engineering solutions. It's the hidden plumbing that forces theoretical math to survive the brutal realities of hardware.
And that leads to a deeply provocative thought. Today, we've seen how stripping away traditional, proper statistical rules like calculating the mean for normalization or keeping sentences in neat, perfectly organized rows actually unlock the true, scalable power of AI.
Yeah.
It forces us to ask, what other foundational rules of computer science and mathematics are we strictly obeying right now that are actually the very things holding back the next massive leap in artificial intelligence?
Are we building the bridge the best way possible, or are we just building it the way we always have? That is a phenomenal question to chew on. Thank you all for taking this deep dive with us. Keep questioning the invisible structures around you, and we'll catch you on the next one.